So one of the really important things that we need to consider when we are going through a geospatial analysis is which type of data model we need to use for the criteria that we're looking for. So as you know, we have been working with vector models in the previous weeks, and now we have started working with raster models. And so I just want to go over data model conversions. Sometimes you might start with vector files and decide that you need to convert them to rasters and vice versa. And then in Lab 10, we're going to be converting from raster to vector, and I'll get into that in just a moment. So many features can be represented as rasters or vectors, and you'll want to select the data type based on the nature of the data and the analysis you want to perform on it. You can convert data between rasters and vectors, but the nature of the data will be very different. Some problems associated with conversion is whenever you convert data from raster to vector or vector to raster, you will degrade the data by some amount. Some issues that you might come across are loss of detail, loss of accuracy, stair stepping, which you'll see mostly in raster to vector. So remember that rasters are represented in a grid of cells, and each cell has a different value associated with it. So when you're then converting your rasters into vector, sometimes your lines are going to look like there's like a stair step. And so there's processes where you can then smooth out the vector lines, but we won't really be covering that in this course. And then also, of course, the issue of changes to the original data. Here we have an example of watersheds in Humboldt County represented as shapefiles. And then we have used the feature to raster tool, which will convert these polygons to rasters. So this image here looks very similar to the one above, but it's now represented as a raster file. So when choosing between data models, a common saying in GIS is raster is faster, but vector is correcter. So some more detailed guidelines on what kind of model you want to choose are, so for raster data, it's useful when you're working with continuous data types like elevation, slope, and satellite photos. It's good for a large area analysis. And it's also good for surface or terrain analysis, mathematical modeling, and when spatial detail isn't important. And then vector data is useful when you're working with discrete data types such as trees, buildings, property boundaries. It's good for small study areas, and when spatial detail is important. When close enough isn't really good enough. It's also great for when topology is needed for the analysis. Some other factors that can influence your decision include available storage. Some raster files are really large, which I'm sure you've noticed when you've been downloading them and trying to recompress them. Also, when different expected types of analysis, some tools only work with raster or vector data. And also, of course, the expertise of the human operators. Maybe you might be more familiar with vector processing or raster processing. And then also the level of accuracy that is desired is also needs to be considered. So in Lab 10, we'll use raster to polygon. It's the opposite of this function that we see in the slide, but very similar. So basically, we'll just be going from raster to vector. And so in the lab activity, we want to know where the suitable habitat for the tree Trephilus trefili overlaps with the salamander conservation areas. And since our salamander conservation zones are in vector and our Trephilus trefili habitat is in raster, we need to convert one or the other between data models in order to be able to complete this analysis. And so you'll be switching into a vector model, like I was saying, and this is going to allow us to use overlay operations that work well with vector models, where you might not necessarily be able to do that same kind of overlay operation with a raster file. Okay, so just like in vector analysis, raster operations or functions are characterized by their spatial scope. They can be classified according to the area of input data used in determining the values at output locations. Operations may use mathematical operators, like the Boolean and comparison operators. They might convert meters to feet in a local operation. It also doesn't have to be simple addition. It can be a more complex mathematical function on a cell-by-cell basis. And it also doesn't have to be mathematical. It can be a logical operator like and or. So the spatial scope for raster analysis is the area of the input data that are used in determining the values at output locations. Local operations are the most basic that we've talked about so far, and the data at only one input location is used to determine the value at a corresponding output location. Global operations use data from the entire input layer to determine each output value. And the neighborhood or focal function use data from both an input location plus nearby locations to determine the output value and is defined by the window. A window is a configuration of raster cells used to specify the input values for an operation. The window is positioned on a given location over the input raster and an operation applied that involves the cells contained in the window. The result of the operation is usually associated with the cell at the center of the window position. One of the most powerful things we can do with rasters is run mathematical operations on them. These and other raster calculations are performed regularly by GIS professionals. The concept of raster math was introduced by Dana Tomlin and Joseph Barry in the 1970s. The idea was that you could perform math on a raster on a pixel by pixel basis. Some examples might include adding rasters with a number of various species together to find the total number of species. You can average multiples of temperature rasters to find the mean temperature for a time period. Or you can divide the total number of birds observed over a year by the number of visits to obtain a raster with the number of birds per visit. Here's another real-world example on how to use map algebra. So this is an expression that someone used to calculate overall fire hazard. So we have three separate layers, one representing fuel density hazard, another slope hazard, and the third vegetation type hazard. And they have added them all together to get an overall fire hazard. The resulting layer will show where all the fire hazard areas are. So this is very powerful stuff. Any mathematical equation you can think of, you could plug it into the raster calculator. So just to give you another visual aid in the way that map algebra works, especially when calculating raster files, is you have two separate raster layers that you are going to be using in your formula. And so basically the cell that matches up with layer A and layer B is then going to be calculated. So you can see here we have 10 in this corner cell and 4 in this corner cell for the input layers, and if we are going to be multiplying them, 10 times 4 equals 40, which is going to be the new cell value in your output raster data set. In addition to map algebra, reclassification is also a major component of raster analysis. Raster reclassification assigns output values that depend on a specific set of input values. Reclassification is mostly either reclass by table or reclass by range. In this lesson, we'll just cover reclass by range, and you'll be going through a reclass by range exercise in Lab 10. This process is similar to a reclassification by a table, except that a range of values appears for each entry in the reclassification table. Each range corresponds to an output value. This allows a more compact representation of the reclassification. This type of reclassification can also apply to the automated reclassification rules of equal interval, equal area, and natural breaks. So for example, if we were to start with the raster layer, we would want to specify a range, and then if the cell value falls within the range, it gets reclassified to the value specified. So here we have our raster values, and then if we were to reclass by range, anything that is a cell value of 0 to 1.5 is going to be assigned a 0. Anything 1.5 to 3.5 is a 1. 3.5 to 10 is also a 0, and no data is also a 0. So once you reclassify, your resulting output layer is going to look something like this in its grid. And again, remember in ArcMap, reclassified values must be an integer or no data. Okay, so let's say that I want to reclassify a slope layer that I've created where I've determined the suitable slope is going to be any cell value that has a value greater than 20. And so my first class break, I'm going to be looking for anything that is less than 20. So anything that is less than 20 is going to be assigned a value of 1. So I'm going to set that break at 19.999. So if I were to be looking for anything that is 20 and or equal to or greater than 20, then I would set that class break at 20, but I'm not. So I'm looking first of all for anything that is less than 20, which will be unsuitable habitat. So I have that set at 19.999. And so then all of the remaining habitat, which is going to be greater than 20, is going to be assigned a 0. And so my resulting layer is going to have just 2 colors in it. But really quickly, this is going to be a similar interface that you'd see if you'd hit the classify button on the symbology tab. And so we're not throwing features into a class and saying symbolize them all this way. What we are saying is if a cell falls into one of these classes, this is what I'd like for you to assign the output cell. So again, anything that is less than 20, 0 to 19.999 is going to be assigned that 1. And then anything that is 20 and greater, which would be that suitable habitat, is 0. And we could see that here where we have our 2 class breaks in our histogram. We had that first break of 19.999, and then we have that second part of the range, which is everything else, which is above 20. So all the cells that meet the criteria are now being represented here. So we could see that anything that is suitable, which has that range of anything 20 and above, is red, and anything that does not have a suitable slope or any cell is going to have that designation of 1. So all of my suitable areas are represented in red with a cell value of 0 now, and anything that is unsuitable is represented in green with the cell value of